Hello, what we'll be doing today is we'll be taking a look on how to take a 2's complement from an integer number, and then we will be looking at how to convert to and from 32-bit IEEE 754 form. So let's start. First, we'll be reviewing how to make a 2's complement basically for a number. And so let's start with -50 over here. So what we're going to do is we're going to take -50. And then what we're going to do is we're going to first convert it just the 50. So we're going to forget about the negative. We're just going to make 50 into its binary form. So how do we make 50 into its binary form? So the way I recommend doing this is you're going to take 50 and you're going to divide it by 2. So 50 divided by 2 is equal to 25 and remainder is 0. Then you're going to take 25, we're going to divide it by 2, and that is going to give us our 12, remainder of 1. 12 divided by 2 is equal to 6, remainder of 0. We carry on. So 6 divided by 2 is equal to 3, remainder 0. 3 divided by 2 is equal to 1, remainder 1. 1 divided by 2 is equal to 0, remainder 1. And here we're going to stop. And so 50 in binary is, you're going to read this way up. So 50 in binary is actually equal to 110010. Okay? And now what we're going to do is, because this is 8 bits, 8-bit binary, what we want to do is we want to make sure that what we have over here is 8 bits. So what we're going to do is we're going to count. So 1, 2, 3, 4, 5, 6. So here we have 6 bits. So then we're going to add 1 on the front as 0, and that is just to say that we're just padding it, because if you add a 0 in the front, that does nothing. And then we're going to add another 0. And just as a reminder, like not a reminder, but just something interesting to consider, is that this bit over here actually just represents the sign. And we're going to see how that works soon. But just keep that in mind. Just looking at the left, I quickly also want to mention the algorithm I'm going to use. And this is just how you convert from any base, but in particularly base 2. And just to show you what the algorithm is, I kind of did it without really explaining. So you're going to take your number, and you're just going to divide it by 2. Then you're going to see what that equals to, and put the remainder onto the right. So here we got 25, remainder 0. Then what I'm going to do is I'm going to take the number I got equal to, and put it right over here, and then again divide it by 2. So here we got 25 divided by 2 is equal to 12, and with a remainder of 1. So we're going to keep that here, and then again we're going to take 12, we're going to plug it into here, and then again divided by 2. So you're going to do this until you reach basically 0. When you get 0, 0 divided by 2 is always going to give you 0 with a remainder of 0, and that just isn't helpful. And then the number you get is going to be read from bottom. So again, 1, 1, 0, 0, 1, 0. So here it is. Now what we're going to do to make a 2's complement is, the first thing we're going to do is we're going to flip it kind of. We're going to take the not operation there. We're going to flip all the bits. So let's do that. So if we flip all the bits, we're going to get 1, 1, 0, 0, 1, 1, 0, 1. So our first step is just figuring it out. Our second step is flipping it. We're going to flip this number. And the third step is we're going to add 1. So we're going to add 1. So let's do that. 1, 1, 0, 0, 1, 1, 0, 1. We're going to add 1 to that. So 1 plus 1 is 2, but this is binary, so we can't have 2, so it's going to be 0. We're going to carry it over, so it's 1. So then you're going to add that 1. We're going to get 1, 1, 1, 0, 0, 1, 1. And there you go. That's going to be your 8-bit 2's complement for -50. So this is, in a way, how your computers use -50 when you enter it as an integer. And hopefully that made sense. So now let's do some more examples just to practice. Next, we have -96. Oh boy, we're gonna have a fun time converting 96, but it's gonna be good practice. So I'm sorry, let me just erase this quickly. There you go. So we have -96. So again, the first step is to write it out 96 in its in its just binary form. And I also quickly want to just, no, I'll do it later, sorry. So we're going to start 96 divided by 2 is equal to 48 with a remainder of 0. 48 divided by 2 is equal to 24, remainder of 0. 24 divided by 2 is equal to 12, remainder of 0. 12 divided by 2 is equal to 6, remainder of 0. 6 divided by 2 is equal to 3, remainder 1. The remainder 0 is what I meant to say. 3 divided by 2 is equal to 1, remainder 1. 1 divided by 2 is equal to 0. 0, remainder 1. So here we go. That's the 96. We're going to get 1, 1, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. Perfect. So 1, 2, 3, 4, 5, 6, 7. Then again, we're going to pad it in the front with a 0. Again, this just represents that this is positive. In this case, you could think of it like that. This says that this is positive 96. Now, that was our first step. Now, our second step, again, is to just flip it. Flip all the bits. So 0 becomes 1s and 1s become 0. So 1, 1, 1, 1, 1, 0, 0, 1. Finally, on step 3, we're going to add 1 plus 1. So it's going to be 1, 0, 0, 1, 1, 1, 1, 1 plus 1. So let's add it. So we're going to get 0. Put a 1 over here. 1 plus 1 is 2. So you're getting 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1. And there you go. That's going to be our number. And again, just as a fun fact, you see that it's negative because this 1 represents negative 1. Perfect. Now what we're going to do is we're going to represent 10 as a 2's complement. And what you're going to see is it's actually going to be very simple because it is a positive number. So 10, again, first step is just going to be finding what this is. So let's do it. So 10 divided by 2 is equal to 5, remainder 0. 5 divided by 2 is equal to 2, remainder 1. 2 divided by 2 is equal to 1, remainder 0. 1 divided by 2 is equal to 0, remainder 1. So 10 in binary is just 10, 10, 10, 10, and then we need to pad it in the front. So 0, 0, 0, and finally another 0, and there we have it. That's going to be that's its bit 2-bit complement. This tells your computer that we have a 10 in our integer. Cool. So now that we learned how to convert something from decimal into its 2 bits, 8 bits, 2 complement form, 8-bit just represents, there are 8 bits representing it. That's why I'm kind of mixing it up. Now let's try doing the opposite. Let's take some 8-bit and try to convert it, see what that actually is equal to. And so what we're actually going to do is we're just going to follow the exact reverse process of what we did before. So first what we're going to do is we're going to have 1, 1, 1, 0, 0, 0, 0, 0. Just again, this 1 represents that this is a negative number. And that's how we kind of can tell to ourselves that, yes, this is in fact negative numbers. So we kind of go through this whole process to find what its positive value is. So then we could put just a negative in front of a decimal. You'll see more. I'll explain this more when we get to this example, because as you see here, the 0 represents this as a positive number. You see that it's going to be very, very simple. Okay, so the first step, as I said, if you're trying to find what this is in decimal, so you're going to subtract 1. So we're going to subtract 1. So what's going to happen then is, let's subtract 1. So this becomes 0, this becomes 2, but then we need to take 1 from it, so it becomes 1. So this is going to become 1, this is going to become 1, this is going to become 1, and this in the end is going to become 2. So 2 minus 1 is 1, 1 minus 0, 0, 1, 1, 1, 0, 1, 1. Then we're going to flip all of it, just as we've done before, so it's going to become 0, 0. So that's going to be our first step, and then our second step is just to flip the bits like we have done before. So it's going to become 0, 0, 0, 0, 0, 1, 0, 0. So then what we're going to do is we're just going to see what this number is. And we do that, if you don't remember, we're going to, each of these is just like thinking. The way you can think of, even in decimal, I'll just quick tangent here. So in decimal, when we write out a number, so let's say 256, with this number, let me make my 6 pretty nice, 256, what this number actually represents is 2 times 10 to the second, plus 5 times 10, 10 to the first, plus 6 times 10 to the 0. And as you see, because we're working in decimal, we have a 10. That's going to be our base 10. And as the numbers increase, what happens is that we just raise 10 to the bigger power. And so that's the exact same thing that basically happens in decimal. But in decimal, what makes it very easy is that it's either 0 or 1. So here you see how we can have 2, 5, so that can kind of make it harder, but here it's very simple. So then we can see that this is going to be 2 to the power of 0, but 2 to the power of 0 times 0 is just 0. So when you add 0, it'll give you nothing. So basically, you can just go down the list and see at what power of 2 you will be. So this is going to be to the power of 0, to the power of 1, to the power of 2, to the power of 3, to the power of 4, to the power of 5. So we're going to get 2 to the power of 5, and this is 32. So now you know that this represents 32, and now you know it's negative, so it's going to be negative 32. So this is equal to negative 32. Cool. Let's go on to the next example. So we're going to get 1, 1, 0, 0, 1, 1, 0, 0. So again, first step is to subtract 1. And again, if you can remember how to find from a decimal to its 8-bit 2 complement, you can just remember that going the opposite way, it's the exact opposite process. So let's do it. 1, 1, 0, 0, 1, 1, 0, 0, minus 1. So this is going to become 2, going to become 1, and this is going to become 2. So we're going to get 1, 1, 0, 1, 0, 0, 1, 1. So then let's take a look what this happens. So then we flip all the bits. We're going to get 0, 0, 1, 0, 1, 1, 0, 0. So now what we need to do is we need to figure out what this is in decimal. So this is 2 to the power of 0. And again, as I just said, we really don't care about the 0. So then we see that this is to the power of 0, to the power of 1, to the power of 2. So we do care about 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. We do care about 2 to the power of 4. And then over here we have 2 to the power of 5. So we do care about 2 to the power of 5. And what do I mean by we care? That means that this, we're going to add 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 2, because you're going to multiply them by 1. So then when you're actually, if you take that very large sum, you're going to see that this is all that really matters. So if we do that, then 2 to the power of 5 is 32. 2 to the power of 4 is 16. And finally, 2 to the power of 2 is 4. So this is 52. And now we remember that this is supposed to be a negative number because of this. So now we know that this is equal to negative 52. Cool. Our last number is 0, 1, 1, 1, 0, 1, 1, 1. 0, 1, 1, 1, 0, 1, 1, 1. Perfect. So now that we have this, what we need to do is we kind of see that right now this number isn't negative. So actually, all we need to do is, because this number is not negative, that means that this is kind of its true representation just in decimal. We don't need to convert anything anywhere. So all we really need to do is we need to see what this is in decimal. So let's do that. So again, this is going to be 2 to the power of 0. This is 2 to the power of 1, 2 to the power of 2. We don't care about 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and 2 to the power of 6. So then what we're going to be doing this is equal to 2 to the power of 6 plus 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0, which is then in turn equal to 2 to the power of 6 is equal to 64. 2 to the power of 5 is equal to 32. So 32 plus 16 plus 4. 2 to the power of 1 is 2, so 2. And 2 to the power of 0 is 1, plus 1. Okay, let's add this all up. So this is going to be equal to 96. plus 4 is 100. 100 plus 16 is 116, so it's going to be 119. So this is simply equal to 119. Cool. We figured out how 8-bit 2 complements form works. Now let's move on to some of the big stuff. Let's see how IEEE 754 works, how we convert to it and how we convert from it. So what I'm actually going to do is I'm going to start on how to convert from a specific number from like a given IEEE 754 to an actual number. So the first number that we will be working with is 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I made a mistake. I apologize. Let me just continue. So there should be 23 of these, and I'll kind of explain why that is. 1, 2, 3, 4, 8, 12, 16, 20, 23. Perfect. So now let's take a look at, so this, all of it, this is what the computer would see if you're trying to initialize a float number. So then this over here is called the sign bit. And all this bit says is whether our number is going to be positive or negative. So since we see that that's a 0, that tells us that our number is actually just going to be positive. So the 0 represents that it's positive. Next, what we have is we have the exponent. This is the exponent. Exponent. And this tells us by how much we kind of multiply our number. 2 to the power of what? We're going to multiply our number. Finally, this gives us our decimal. This is called the mantissa. Mantissa. And what the mantissa tells us is basically that's the actual number. That's what we are going to multiply the exponent by eventually to actually get what we're looking for. Cool. So the way we're going to start this off, so we already know the sign. Next, what I want to do is I want to find the exponent. And so the way you kind of find the exponent is you know that the exponent minus 127 should equal to this. And this is, so let's look at it. Let's quickly convert 111 into its decimal form. So this is, sorry, this is going to be, I'm just going to add it right away. Sorry. So it's 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6. I counted wrong. 1, 2, 3, 4, 5, 6, 7, 8. There you go. So we just know that it's going to be 2 to the power of 7 plus 2 to the power of 6 plus 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. So let me get out my calculator and quickly just calculate this. You can follow along, I guess, at home and pull out your calculator and also try to figure this out. So what we're going to be doing now then is once we've calculated that, we should get an answer. And wait, I know what I did wrong. Sorry, I was just checking and I got some weird answers. That's why I was kind of so it's hopefully you guys caught this mistake at home, but this is gonna actually equal to this 2 out of 7 is out of here. This shouldn't be here. This is just 2 to the power of 6, and so on and so forth. And so the answer that we should get is 127. And earlier I said, so this represents, so the way we know what we raise our power to is actually it's just 127 minus 127. And again, this bit over here kind of represents the sign. Is this positive or is this negative? So to what power we're taking our actual, to what power we're going to take it. Is it a positive power or is it a negative power? Okay. So then what we're going to do now, and the way it represents itself, just as a quick note, is this going to be smaller than 127 or bigger than 127 or equal to 127? So if this is actually a 1, I kind of misspoke earlier, but if this is a 1, the number you're going to get is always going to be bigger than 127. And what that would mean is that you're actually going to get a positive exponent. If this number is 0, for instance, and you don't have just like 1, 1, 1, 1, 1, for instance, if we had 1, 0, what would happen is that we would get something smaller than 127, so we would get a negative exponent. But the basic gist of it is you calculate what this exponent is, and then you do e minus 100, or sorry, the exponent, which is this, minus 127, and that will give you how many basically decimal places you're moving over. We'll see soon. But in this case, we get 0. And I'll show you what would happen if you have like 1 or 2 afterwards. Now finally comes the tough part. We're going to have to deal with our mantissa. So with the mantissa, just to have like more precision, it's always assumed that this mantissa is actually always has a 1 in front of it. So this is actually represented by 1 times 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and so on and so forth. Okay? So then what we're going to do is we're going to just see what this number is now. So the way you see how this number is you're going to split up your mantissa into 2 different parts. You're going to look at this part, and then you're going to look at all of this part. And just as a quick note, in this case, because our exponent is 0, we wouldn't move it. But if our exponent, for instance, was 1, that will represent that we're multiplying this by 2 to the power of 1, and our decimal would be moved over 1 to the right. Or if this was 2, if the exponent was 2 here, like the result would be 2, then we would move it 2 over. On the other hand, if we got a negative number, so for instance, our exponent ended up being, like the subtraction after subtraction negative 200%, ended up being negative 2, for instance, e to the power of 2 to the power of negative 2, what would happen is we would transfer our decimal place 2 to the right, to the left. I don't know my lefts and rights, guys. I'm sorry. So, but in this case, because it's 0, we just keep it as it is. So then what we're going to do is, again, we're just going to separate our what's before the decimal and what's after the decimal. And we're going to kind of separately convert them to what is it called? We're going to separately convert them into decimals. So then first we convert the 1, and that 1 in front is just a 2 because it's 2 to the power, it's just 2. That represents a 1. I don't know why I said 2. Sorry. This is a 1, and it's 2 to the power of 0, which makes sense, and that's why it's just 1. So we know that our decimal in the front is going to be 1 point, and again, we know it's positive because of the sign, but it's positive. So it's 1 point, and then we need to convert all of this into decimal. Now, the way we do this is actually very similar. So just before we start, for instance, if I had something like 0.01, the way you convert this into decimal is from decimal to binary, I meant to say, is the exact same way as you convert just regular binary into decimal. So as we saw before, if this is 2 to the power of 0, then this is actually 2 to the power of -1. And this is 2 to the power of -2. So what we're going to have to do is, again, we're just going to have to sum them all up. So again, we can see that this is -1, -2, -3. So -3, we care about 2 to the power of -3, we care about 2 to the power of -4, we care about 2 to the power of -5, we care about 2 to the power of -6, we care about 2 to the power of -7, -8, we care about 2 to the power of -9, -10, 2 to the power of -13, -14. Then we care about -15, -16, -17, -18, and finally 2 to the power of -20. So if we grab our calculator and we actually add all of those up, we can see what we're going to get. I said it over here, -5, -6. You hopefully caught me my mistake as well. This isn't -5, -6. It's actually -7, -8. Did I mess up my whole chain? That's funny. 5, 6, 7, 8, 9, 10. So this would be 11, 12. 11, 12. Here, let me just redo all of it. So again, if we start our count, you're going to get -1, -2. So this is going to be 3, and just know that these are all to the power of -3, -4, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yeah. Now we can grab our trusty calculators and start adding all of this up. So 2 to the power of -7 plus 2 to the power of -8 plus 2 to the power of -11 plus 2 to the power of -12 plus 2 to the power of -15 plus 2 to the power of -16 plus 2 to the power of -15 plus 2 to the power of -19 plus 2 to the power of -20 plus 2 to the power of -22. Okay. Okay. And what we should get is 1.2, and then you're gonna have a lot of zero, like it's gonna be 0.0000477. And most likely that's just gonna get chopped up in the end because it's 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 after. So most likely it'll just get chopped off and you can basically round it to 1.2. But in theory, this does represent 0.2000477. You would see it in your calculator. But then this would be our decimal. Now, let's do another example and see what we get. So here it is. So here's the second number we're going to take, and then we're going to see how to make a number go into its IEEE form. So 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 2, 1, 3, Why don't I just make a random number up at this? I'll make it easier for us actually. So 0, 1, 0, 1, 1, 1. Let's put another one here and then end it off all with zeros. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, comma, 5, 6, 7, 8, comma, 12, 1, 2, 3, 4, 16, 1, 2, 3, 4. I can't count. 1, 2, 4, 8, 12, 16, 20, 1, 2, 3, 23. Perfect. So now again, we're just going to start up with our process. So first we look at our sign bit. Our sign bit is 0, therefore our number is positive. Then we're going to look at our exponent. And we're going to convert that exponent into its the decimal form. So if you remember, so again, this is represents 2 to the power of 0, and then we can go on. So we care about 2 to the power of 0, care about 2 to the power of 2, 3, 4, 5, and 6. So again, we can grab the calculators and quickly calculate that. It's going to be 2 to the power of 6, 6 plus 2 to the power of 4 plus 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 2 plus 1, 93. So we get 93. And so then if we get 93, and what's going to happen is we're going to find out our exponent by doing 93 minus 127. So 93 minus 127 is going to equal to negative 34. So what we're going to do then is now we know that this is negative 34. And basically what that means is that, again, we have a 1.0 here. And that means that we're actually going to be shifting this decimal place, because this is now that we know our exponent. This is, you can imagine that this times 2 to the power of negative 34. So that means we're going to have to shift our decimal place 34 places over to the left. It's a long way to go. So then if we shift it 34 places to the left, what we're going to get is we can still kind of figure out what this is going to be 2 to the power of what. So if we have 0 point and then 33 decimals, and then which ends with our thing, and 33 zeros, yeah. So then this is going to be 2 to the power of negative 34, 2 to the power of negative 34. It's going to be 2 to the power of negative 36, and then it's going to be 36, so 37, 38, 38, 39, 39, 40, 41. So then what we're going to do, again, we're going to grab our calculator and just add that. And what we see as well is that in the front, what we're going to get is a 0. So we know that it's going to be 0 point something. So now we just need to figure out that point something. So 2 to the power of negative 34 plus 2 to the power of negative 36 plus 2 to the power of negative 38 plus 2 to the power of negative 39 plus 2 to the power of negative 40 plus 2 to the power of negative 41. You're going to get a very, very, very small number. It's going to be something, what I got on my calculator is 7.958, and you can continue, but it's 7.958 times 10 to the negative 11. So then that means we're going to have 0 0.000000000, and then we're just going to round it to an 8 here. And there you go. We just converted this number into this IEEE 754 into its decimal number. Perfect. Okay, now let's get to the other side of this. So now that we know how to convert from the 754 form, let's go the opposite way. So now let's say we have something like negative 5.1 that we want to convert into the way the computer would see it in the float point numbers. So first what we do is we get the sign bit, and the sign bit is always easy to get. If it's negative, it's 1. If it's positive, it's 0. So we know our sign bit is going to be 1. Then what we're going to do is we're going to look at this and we're going to convert this into its binary form. What I'm actually going to do is I'm going to be a bit nice to us. And I'm going to make this a neater number. Let's make this into 25.25. Okay, and I promise that this just makes it a bit neater. That's why I'm doing it. So then, the way we convert this is we first take this and we convert this into its binary. And you can do it using the method I taught before, but I just know that 5 is 101, so it's going to be 101 point, and then we need to make the decimal into a decimal binary form. So the way you're going to do that is you're going to take your decimal, so it's going to be 0.25, for instance. You're just going to multiply it by 2. So in this case, we get 0.5. So then what you want to do is you want to kind of truncate this and only take what's after the decimal. So here we get 0.5. So 0.5 times 2 is equal to 1.0. And now what we see is we got 0 here. So the next step in theory would be 0.0 times 2, but that would just give us a 0.0. And now what we're going to do is we're just going to read, this is the decimal we have, it reads down. So that means it's going to be 101.01. So 0.25 is 0.1 in binary. And so this is going to be our binary. So now what we do is we need to see, we always want to have it like, just like in scientific notation where you would always want only one thing in front of the decimal. So for instance, if we had 265, this would be 2.65 times 10 to the 2. You want to kind of do the same thing with this. So to do that, we want to shift it over 2 to the left in front, right here. So then that's going to be 1.01, 1.0101. And then to make these two equal, you still need to multiply it by 2 to the power of 2. So now what we see is we get our exponent over here. So it's 2. So now, if we remember from kind of last time, the way we got our exponent to see what it actually was is we did e minus 127 equals to what this number is. So then we can find e using the same method. So we're going to put 2 here, and then e is equal to 2 plus 127, which means e is equal to 129. So now what we need to do is we need to convert 129 into its binary form. So let's do that quickly. So 129 divided by 2 is equal to is equal to 64 remainder 1. So then what we're going to see is that 64 is a really nice number. 64 divided by 2 is going to give us 32 remainder 0. 32 is going to give us 16 remainder 0. 8 remainder 0. I'm just rushing it along because it's a lot of writing. 4 remainder 0. 2 remainder 0. 2 remainder 0. 1 remainder 0. 0 remainder 1. And so our number then is this. This is our exponent. And we should get 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So now we got our exponent. This is our exponent. And then, do I need to scroll up? I kind of lost us. Yes, I did. So that is our exponent right over there. I can highlight it in red. There it is. I have a perfect, what's called straight lines, as you just saw. Here, I'll put it in a red box. We like red boxes. That's a black box. Let's make it a red box right over here. There you go. So that's going to be our Matissa. And just as again, a reminder, you read bottom to top. And now we're going to go back to this. And then what we do to get our, sorry, that is our exponent. Our Matissa then would be this over here. Again, we don't put in the 1 here. So it's all it's going to be is 0.0101. And then we're going to have to pad the other bits left with zeros. So in the end, if I were to represent this in mantissa form, I would combine everything we have. So first, I would put the sign bit. Then I would put our exponent, which was 1, 0, 0, 0, 0, 0, 0, 1. Exponent, Finally, I would see what our Manti says. So it would be, again, we don't put in the 1, so it'd be 0, 1, 0, 1, and then we pad the rest with zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 4, 8, 12, 16, 20, and we need 23, so 0, 0, 0. And there you go. That would be our number. Okay. Hopefully that made sense. And I'm actually going to stop it here. I'm not going to do a second example. If you guys want a second example, please message me directly or add a comment to the video. And hopefully this helps you. Have a great day, afternoon, evening, I don't know.